So let's continue then with the calculation of pH changes in a buffer solution. So the problem now is, what are the effects on the pH of adding 0.006 moles of HCl, and then we'll do that calculation, and then we'll do the calculation for 0.006 moles of sodium hydroxide. And we're going to add this to a 0.3 liter buffer solution that has 0.25 molar of acetic acid and 0.56 molar of sodium acetate. And of course, the sodium acetate simply gives us the conjugate base of our acid. So the solution then is to judge the effect of adding either an acid or a base on the pH of this solution. So we want to look at this qualitatively first. And in this case, we're given both the acid and its conjugate base concentration. And we recognize that we now have a buffer solution because we have the coexistence of that acid and its weak base in the solution. And that means that we have both the anion, the conjugate base, available to react with an acid, and we have the acid available to react with a base. So we can immediately write down the reaction that we're interested in here. We have the weak acid, and we've got the reaction with water to produce the anion, CH3COO, plus H3O+. To calculate the pH, that's pKa plus log to the base 10 of the concentration of the conjugate base divided by the concentration of the weak acid. In this case, we have our pKa, which is always the case for this acetic acid dissociation. That's 4.74. And then we have the log of the ratio of the acetate anion. That's 0.560. That's given to us in the problem, divided by the molar concentration of the acid, 0.250. And so when we execute that calculation, that gives us 4.74 for the pKa plus 0.35 for the log of the ratio of the concentrations, and that gives us an initial pH for this solution of 5.09. So that's important. The first thing we have to do in a buffer calculation is to determine what the pH of the solution is before we add either the acid or the base. So now we're going to consider first the addition of the acid, and that is we're going to add 0.006 moles of HCl to our buffer solution. And the first point to recognize is that we have to calculate the number of moles of each species involved in the reaction, because the addition of the strong acid results in the neutralization through the acid-base reaction going to completion, driven downhill by that large release of free energy. So let's do that. The reaction we want to consider then is the reaction of this quantity CH3COO. That's the base. That's the conjugate base of the weak acid. And we're going to attack this with 0.006 moles of H3O+. So the first thing we have to focus on is, because we're adding the acid, we have to look at how it's going to attack the base. And the base in this solution is this acetate anion. So that H3O+ goes after that base with a vengeance, producing CH3COOH, which is the weak acid, plus H2O. And I don't write that as an equilibrium because the reaction goes completely to the right. And this corresponds to the weak acid reaction driven backwards. In other words, when I have my acetic acid in water forming that conjugate base and H3O+, what this reaction is doing by driving acid into the reaction is that I'm shifting it from the right to the left, as Le Chatelier tells us, that that solution is going to respond to that implied stress by adjusting such as to minimize the difference. But no equilibrium is involved. That's the important point in calculating these buffer problems. First thing we do is calculate the pH before we've added anything, but then we have to count the number of molecules that are reacting, which means we need to know the number of moles. So in this case, we've got 0.3 liters and we have 0.56 molar of our anion. and that gives us 0.168 moles. So we've counted the number of anions. We have to do exactly the same thing with our weak acid. We have the same 0.3 liters, but now we have 0.25 molar, so that gives me 0.075 moles of the acid. Well, that's interesting because now the problem says that we're going to add 0.006 moles of H3O plus of the acid. So when I work out this, I recognize that in this solution I'm going to drive 0.006 moles of H3O plus. Now, a very important point here is that this is not a Rice table. We don't have any equilibrium involved in this. We are adding one H3O plus and we're taking out one conjugate base. So it's a simple arithmetic problem. So the change then is that we're going to steal one conjugate base for every H3O added, so that's a minus 0.006. But because it's reacting with H3O plus, that's exactly the same change, and we're adding 0.006 moles of the weak acid. So the final buffer amounts, we simply execute the addition of minus 0.006 to 0.168, and we get 0.162 moles of the conjugate base after the reaction. Exactly the same logic applies to the weak acid. We've got 0.006 moles added to 0.075, and that gives us 0.081 moles of the weak acid. So the concentrations, then converting it back to molar, is 0.54 molar because we have 0.162 moles divided by 0.3 liters for the conjugate base, and for the conjugate acid, it's exactly the same calculation, but in this case we have 0.081 moles, which gives us 0.270 molar. Then the next thing we must do is to do an acid equilibrium calculation so that we can redetermine the pH using this new equilibrium concentration. Now we can do this with a Rice table, but because we recognize that this is the buffer solution, we've got a very quick way to do that pH calculation, and that's our good old Henderson-Hasselbalch equation. pH is equal to pKa plus the logarithm of the concentration of our conjugate base divided by the concentration of our weak acid. We know the pKa of that, that's 4.74, and we've already now gone through the calculation of our new conjugate base concentration and our weak acid, so we can insert those numbers. That's a logarithm of 0.54 divided by 0.27, and when we do that calculation we have 4.74 plus 0.30, and that is equal to 5.04. A small change in pH resulting from now the addition of the acid. So the conclusion is that the addition of 0.006 moles of HCl lowers the pH from 5.09 to 5.04. A tiny change. This is the point of the buffer solution. It protects that solution against changes in pH resulting from the addition of either an acid or a base.